Hi everyone. In this video we're going to be going over a past physics Regents problem involving standing waves. So it says, a musician plucks a 0.620 meter long string on an acoustic guitar as represented in the diagram below. The plucked string vibrates, producing a musical note called G. The waves traveling along the vibrating string produce a standing wave with a frequency of 196 Hz. So I started by circling my numbers and units and boxing some keywords. 0.620 meters, I can't really list that as a variable yet because it's not actually a full wavelength, so we'll come back to that. But 196 Hertz is my frequency, so I'll write that down for later. And then they mentioned that this is a standing wave, which is an important concept. So I wanted to review a little bit about standing waves before we move forward with the problem. So this is a diagram of a standing wave. That's something that it will typically look like. Sometimes you'll see one solid line and one dotted line. Sometimes you'll just see two solid lines like this. But anytime you see a standing wave or they mention a standing wave, it's expected that you know how to count nodes, antinodes, and wavelengths. So these red dots represent nodes. Basically, you're just looking for points where the two lines overlap. But in physics terms, they might say that it's maximum destructive interference, or they might refer to it as having displacement of 0. You also need to know how to count antinodes, or at least identify where they are. Antinodes are the points where the two lines are farthest apart. You would see just kind of, it naturally divides itself into these 4 sections. Each one of these sections in the middle of it is one of the antinodes. In physics terms, again, that's called maximum constructive interference or maximum displacement of the wave. And then, of course, you also need to be able to count wavelengths. It's not actually anything different than a regular wave. It still has that same shape. If I start at 0, I would have to go up to the crest, down to the trough, and then back to 0. And that would be a full wavelength. But when you're counting standing waves, it can be a little weird to kind of keep making that shape when you have 2 of them overlapping. So something that might be easier is just counting antinodes and then dividing by 2. For example, in this diagram, I just see 1 antinode, so it's actually only representing half of a wave. In this diagram, I see 2 antinodes, and then I divide by 2, and that means there's 1 wave being shown. In this diagram, 1, 2, 3 antinodes. If I divide by 2, that gives me 1.5 waves. Alright, so let's move back to the problem. For question 81, it says, on the diagram of the standing wave in your answer booklet, label one node with the letter N and one antinode with the letter A. Basically, the node is any place those two lines overlap, so here or here would be my node, and then antinodes are in the middle. So aim as close to the middle of this diagram as you can. I would write A, and then here I would write N. Again, of course, you could also put that here. That would be fine. Question 82 says, determine the wavelength of the standing wave on the 0.620 meter long vibrating string. Again, keep in mind that the number given here is not actually the full wavelength because, like we said, we only have 1 antinode. So if I divide by 2, that means I only have half of a wave, or half of a wavelength. So if I only have half of the wave shown, I would have to multiply this number by 2. And that's how I would get my answer, 1.24 meters. And that's my true wavelength. Question 83 through 84 says calculate the speed of the wave traveling on the vibrating string. And of course, I have to show my work. I underlined speed because that's what I'm solving for, but there isn't really anything else noteworthy here in this question. I'm just going to be taking my information from the previous parts of this question. So we had already written down that F is equal to 196 Hertz. We just calculated that wavelength is equal to 1.24 meters, and I'm solving for velocity. That leaves me with this formula, V equals F times lambda, and I just multiply my two numbers together, and I get 243 meters per second. I got 243.04 in my calculator, and I just rounded to 243. Question 85 says, describe what happens to the frequency when the musician shortens the vibrating portion of the string by pinching the string against the fingerboard while the string continues to vibrate. This may feel like a lot, but keep in mind, anytime they say describe what happens, all they want you to do is write increase, decrease, or remains the same. So even if you don't understand the rest of the problem, anytime they want you to describe something, you're kind of automatically given these three choices. So you can always just give it a guess if you're not sure. But in this case, we want to know what's going to happen specifically to the frequency. Will it increase, decrease, or remain the same when we make these changes? So the rest of the question is kind of wordy, but essentially they just want to know what's going to happen when you shorten the vibrating portion of the string. The string starts out like this. These two red dots represent the nodes. Basically, what would happen if I just slid one of those over, made the string shorter? In other words, creating a shorter wavelength. How would that affect the frequency? If you remember that frequency and wavelength are opposites, you'll know the answer. It's going to give you a higher frequency. You can look at the formula that we used, V equals frequency times wavelength, and solve for frequency or wavelength, and that will help you realize, according to the formula, why these two physical quantities are opposites. But for the purposes of this question, as long as you know that they're opposites, all you have to do is say that the frequency increases or a higher frequency, and that's going to be your answer.